To do this, we must first dismantle the most persistent illusion of our daily lives, the sensation of now. When you sit in a room and switch on a lamp, the illumination appears instantaneous. You flip the switch, and the light is simply there, washing over the furniture and the walls, without any perceptible delay. If you wave your hand in front of your face, the image of your movement seems to register in your mind at the exact moment it happens. This synchronicity is the foundation of our existence. It allows us to catch a ball, drive a car, and converse with one another. It convinces us that there is a universal present moment shared by everything we can see. But this is a deception, born of proximity. We live on such a microscopic scale, clustered so tightly together on the surface of this rock, that the travel time of light is rendered irrelevant to our biological senses. In the vast architecture of the cosmos, however, there is no such thing as an instantaneous event. Light is not a magical presence that fills space immediately. It is a traveler. It is a physical courier carrying a packet of information, moving at a finite speed. Fast, incredibly fast, but finite nonetheless. It travels at roughly 300,000 kilometers per second. On Earth, that speed is effectively infinite. But once we step off the surface of our planet, the distances become so staggering that even light begins to lag. Consider the Moon, our nearest celestial neighbor. It is close enough that we have walked upon its surface, yet even here, the illusion of now begins to fracture. The light reflected from the lunar surface takes 1¼ seconds to cross the gap to Earth. When you look up at the Moon, you are not seeing it as it is. You are seeing it as it was 1 second ago. If a meteor were to strike a crater on the Moon, you would not witness the impact until after it had already happened. The event and your perception of the event are separated by the unyielding barrier of time. Move further out to the Sun, it lies 150 million kilometers away. The light that warms your skin on a summer day did not leave the solar surface at the moment you felt it. It began its journey 8 minutes and 20 seconds prior. If the Sun were to suddenly vanish, extinguished like a candle, we would remain blissfully unaware for over 8 minutes. We would still see its light, feel its heat, and orbit its gravitational center, completely ignorant of the fact that the star we depend on was already gone. We are perpetually trapped in the past, viewing a history that has already been written. As we look deeper into the realm of the stars, this lag shifts from minutes to years. When you locate the nearest star system, Alpha Centauri, you are seeing light that has been traveling through the void for over 4 years. If there were a civilization there, looking back at us with a telescope equal to our own, they would not see us as we are today. They would see a world preoccupied with the events of 4 years ago, in the light of our current moment having not yet reached their eyes. And this is merely our front porch. The galaxy itself is a spiraling city of stars spanning 100,000 light years. To look across the disk of the Milky Way is to look back to a time when human beings were just beginning to migrate out of Africa. To look at our nearest major galactic neighbor, Andromeda, is to capture light that has been traveling for 2.5 million years. Light that began its journey before the genus Homo even existed. This realization fundamentally changes the nature of astronomy. A telescope is not merely a camera. It is a time machine. It does not simply magnify distant objects. It drills a core sample into history. The further away an object is, the further back in time we are seeing. This creates a strange paradox in our observation of the universe. The deeper we look, the younger the cosmos appears. When we look at galaxies billions of light years away, we do not see them as they are today, aged and evolved. We see them as they were in their infancy. We are watching them form, watching their stars ignite, watching a version of them that likely no longer exists. His relationship between distance and time is the primary tool we use to understand our origins. In theory, if we could look far enough, we could look all the way to the edge of the observable universe, we should be able to see the beginning of time itself. We should be able to watch the universe being born. However, the universe does not make this journey easy. The light that carries this ancient history does not arrive at our telescopes unchanged. It has to traverse a cosmos that is not static, but dynamic and expanding. And this expansion distorts the message in a way that makes the oldest secrets the hardest to read. To understand this distortion, we must understand the nature of light. Itself, light travels in waves, like ripples on the surface of a pond. The color of the light is determined by the length of these waves, the distance between one peak and the next. Blue light has short, energetic waves, bunched tightly together. Red light has longer, lazier waves, stretched out. Our eyes are tuned to a very specific, narrow band of this spectrum, a tiny window of reality we call visible light, ranging from the deep violet to the deep red. But space itself is stretching. Since the Big Bang, the fabric of the universe has been expanding, pushing galaxies apart and stretching the void between them. When a photon of light leaves a distant galaxy and begins its journey toward Earth, it must travel through this expanding space. As it travels, the space it moves through stretches, and as the space stretches, it pulls the wave of light along with it. A wave that started as high-energy blue light is gradually pulled apart, its wavelength lengthening as it crosses the billions of light-years. It shifts from blue to green to yellow to orange and finally to red. This phenomenon is known as cosmological redshift. It is the signature of an expanding universe, and it is the primary reason the deep past is so difficult to see. The further back we look, the more space the light has traveled through, and the more stretched it has become. For the most ancient objects in the universe, the first stars and the first galaxies, the light has been traveling for over 13 billion years. By the time it reaches us, it has been stretched so severely that it has been pulled completely out of the visible spectrum. It is no longer red, it has become infrared. This is the great cosmic fading. The universe is not actually dark, it is blazing with the light of ancient creation. But to our biological eyes, and to the optical telescopes we used for centuries, that light has become invisible. It has shifted into a wavelength we cannot naturally perceive, becoming a ghost frequency that passes right through us. We look at a patch of dark sky and see nothing, not because there is nothing there, but because the light of those first moments has been stretched into a form of energy that our eyes were never meant to see. This invisible barrier held back our understanding for generations. We knew the history was there, written in the infrared, but we lacked the ability to read it. We were like a person trying to listen to a radio broadcast but tuned to the wrong frequency. We could see the mature galaxies, the ones close enough that their light was still visible. But the further back we tried to push, the murkier the picture became. The beginning was hidden behind a veil of redshift. However, redshift is only one part of the problem. As we push our vision back toward the beginning, we encounter an even more formidable obstacle than the stretching of light. We approach a time before the stars, a time before galaxies, a time before the universe was transparent. We approach the era where the very structure of matter conspired to block our view. To see the beginning, we must look past the stars we know, past the galaxies we can map, and into a dense primordial fog that ruled the cosmos long before the first sun ever ignited. As we prepare to drift back to that time, we must discard our mental image of the universe as a vast, empty vacuum sprinkled with jewels of light. We must imagine instead a universe that was smaller, hotter, and profoundly different from the cold void we inhabit today. The journey of the James Webb Space Telescope was not just about building a bigger mirror. It was about building an eye capable of seeing heat instead of light, capable of piercing through the dust and the distance to catch those weary, stretched-out photons that have been traveling since the dawn of time. But before we can appreciate what the telescope found, we must understand what it was looking for. We must understand the dark canvas upon which the first brushstrokes of creation were painted. We must travel back to the moment when the lights went out. This transformation of light, from the visible into the infrared, fundamentally alters how we must map the cosmos. We must stop thinking of the night sky as a static dome or a ceiling painted with stars. Instead, we must visualize it as a geological excavation, a vertical shaft dug deep into the bedrock of reality. In an archaeological dig here on Earth, the surface layer holds the debris of the modern world: plastic, alumni, the discarded remnants of the present day. As we dig down a few meters, we encounter the iron and glass of the industrial age. Deeper still, we find the pottery shards of ancient empires, and eventually, the stone tools of our earliest ancestors. The deeper we go, the further back in time we travel. The universe is arranged in exactly the same way, but instead of layers of soil, we are looking through layers of light. The stars we see with our naked eyes are the surface debris the local, modern neighborhood. The faint galaxies we see through backyard telescopes are the industrial age. The deep, swirling spirals captured by the Hubble Space Telescope are the ancient empires. But there is a limit to this excavation. Eventually, The shovel hits a layer so hard and so ancient that our standard tools can no longer penetrate it. This is the horizon where the redshift becomes extreme, where the light from the very first structures has been stretched so thin that it slips through the grasp of traditional optics entirely. For most of human history, this horizon was absolute. We were imprisoned in the visible spectrum. We could marvel at the mature universe, at the grand design of spiral arms and elliptical giants, but the era of their birth remained hidden. It was as if we had been given a photo album of a human life that began at age 30. Cliff could see the adult, fully formed and complex, but the pages containing the infancy, the childhood, and the chaotic adolescence were simply missing. We knew they must have existed. Universes do not spring into being fully formed any more than people do. But the evidence was locked away in a wavelength we could not see. This missing chapter created a profound silence in our scientific narrative. We had theories, of course. We had mathematical models that predicted how the first matter should have clumped together, how gravity should have pulled gas into the first burning spheres. But without observation, without direct visual proof, these remained just stories written on chalkboards. We were blind to the most critical epoch of cosmic history, the moment the clock started ticking for the structures that would eventually become us. To bridge this gap, we had to accept a difficult truth. Our eyes are not the gold standard of reality. Evolution designed our vision to find fruit in trees and track predators in the grass, not to peer across 13 billion light-years of expanding space. To see the beginning, we had to abandon the reliance on light as we intuitively understand it. We had to build an eye that does not see color, but rather senses heat. This is the distinction that defines the new era of astronomy. When light is stretched into the infrared, it behaves less like a beam of illumination and more like a faint warmth. The light from the first stars is no longer a bright shine. It is a thermal whisper. It is a ghostly resonance that has survived. The journey across the entire width of the observable universe, detecting it requires a calmness and a sensitivity that is almost impossible to achieve on the surface of our planet, where the atmosphere glows with its own heat and the interference of civilization drowns out the faint signals from the deep. This is why we had to leave Earth. We had to place our sensor in the deep freeze of space, far from the radiating warmth of our own planet, shielding it even from the sun, to create a pocket of absolute cold. Only in that artificial silence could we hope to catch the faint, stretched vibrations of the first light. We built a time machine consisting of gold-coated mirrors and sun shields, designed to capture the nothingness and translate it back into a picture we could comprehend. As we stare into those deep, dark patches of the sky, we are not looking at empty space. We are looking at a crowded, busy, violent era that has simply faded from view. We are looking at the cosmic dawn, hidden behind the curtain of redshift. The photons are there, washing over us every second of every day, passing through our bodies and our buildings, carrying the images of the first galaxies. They are ghosts of the beginning, traveling endlessly, waiting for an instrument precise enough to catch them and turn them back into history. But as we prepare to dial back the focus, to tune our instruments to this ancient frequency, we must understand that the difficulty is not just about the stretching of light. There is a second barrier, one that is physical rather than optical. As we push back past the first billion years, past the first few 100 million years, we approach a time when the universe was not just invisible to our eyes, but opaque to physics itself. We are moving toward a wall of fog, a time before the universe became transparent. The story of the universe is not just a story of light traveling through space, it is a story of space itself, changing state. Today, we look up and see a clear vacuum, transparent and open. But it was not always so. There was a time when the universe was a thick, blinding smoke, a dense plasma that held light captive. As we peel back the layers of time, stripping away the modern galaxies and the ancient clusters, we eventually run out of clear air. We approach the edge of the Dark Ages, a term that refers not just to a lack of starlight, but to a fundamental difference in the texture of the cosmos. We are about to enter the era where the rules of observation change entirely. We are leaving the clear, open ocean of the modern universe and sailing into a primordial mist. Nothing that James Webb saw is not a void, it is a barrier. And to understand what lies behind it, we must first understand the fog itself, how it formed, how it trapped the light, and how, eventually, it was burned away to reveal the universe we know today. This is the boundary of the known. Beyond this point, the familiar shapes of galaxies dissolve, and we are left with the raw, chaotic materials of creation. Drifting in the dark dot, to understand the nature of this barrier, we must first abandon the image of the universe as a container of empty space. When we look up today, we see vast stretches of nothingness, punctuated by islands of matter stars, planets, and galaxies. The darkness between them is transparent. It allows light to pass unimpeded for billions of years. We take this clarity for granted. We assume that space is, by default, a clear medium, but there was a time when space was not a window, but a wall. If you were to transport yourself back to the first few moments after the Big Bang, or indeed any time within the first 380,000 years of existence, you would not see a black sky filled with stars. You would not see darkness at all. You would be immersed in a blinding, incandescent brightness that filled every corner of reality. There was no here and there, no distinction between a light source and the space around it. The entire universe was the light source. It was a single, continuous storm of energy, glowing with a heat that defied comprehension. This was the era of the primordial plasma. In this early stage, the universe was so hot and so dense that atoms, as we know them, could not exist. The fundamental building blocks of matter, protons and electrons, were too energetic to bond. They moved with frantic, chaotic speed, smashing into one another, rebounding and swirling in a superheated soup of charged particles. It was a state of matter that effectively locked the universe in a cage of its own making. The key to this imprisonment lay in the behavior of the electron. In our modern universe, electrons are tamed. They are locked in stable orbits around atomic nuclei, creating the neutral atoms that make up our bodies, the air we breathe, and the stars we orbit. But in this ancient epoch, the heat was too intense for any bond to hold. The electrons were free agents, stripping away from protons and roaming the cosmos as a loose, electrified mist. This freedom was catastrophic for light. A photon, a particle of light, desires to travel in a straight line. It seeks to carry its energy across the universe. But photons interact strongly with charged particles, particularly free electrons. In this dense plasma, a photon could not travel even a fraction of a millimeter before slamming into a free electron. The collision would scatter the light, sending it ricocheting off in a random direction, only to strike another electron an instant later. Imagine a dense fog on a highway. The reason you cannot see through the fog is not because the light has disappeared, but because the water droplets are scattering the headlight beams in every possible direction, turning the air into a glowing, opaque white wall. The early universe was a cosmic fog, but instead of water droplets, it was filled with electric charges, and instead of a headlight beam, it was the raw energy of creation trying to escape. Light was trapped in a perpetual pinball game, bouncing billions of times a second, going nowhere. The universe was luminous, but it was blind. It held all the energy it would ever possess, yet it could not project an image. It was a glowing, solid block of reality, holding its breath. For nearly 400,000 years, this stalemate continued. Gravity tried to pull matter together, while the intense radiation pressure pushed it apart. The universe expanded, and as it expanded, it stretched. This stretching is the cooling mechanism of the cosmos. Just as a gas cools when it is released from a pressurized canister, the fabric of space-time cooled as it swelled outward. The temperature dropped from billions of degrees down through the millions, and eventually into the thousands. It was a slow, gradual descent, a cosmic winter settling in over the fire of the Big Bang. The frantic motion of the particles began to slow. The chaotic collisions became less violent. The universe was preparing for its first major phase shift, a transformation that would alter the physics of deep space forever. This event is known to cosmologists as recombination, as the temperature dipped below roughly 3,000 degrees Kelvin, comparable to the surface of a small red star. Conditions finally allowed for a truce. The protons, heavy and positively charged, could finally capture the fleeting, negatively charged electrons. The electromagnetic attraction between them overcame the thermal energy that had kept them apart. Across the entire span of the universe, in a process occurring everywhere simultaneously, the free electrons fell into orbit around the protons. This was the birth of the first atoms. Hydrogen, the simplest element in existence, was formed. A single proton, a single electron, bound together in a neutral embrace. The electric charges cancelled each other out. The chaotic plasma, which had been a storm of charged particles, suddenly became a sea of electrically neutral gas. The effect on light was instantaneous and profound. With the free electrons locked away inside these new hydrogen atoms, the obstacles that had blocked the path of the photons vanished. The fog did not just lift, it ceased to exist. The pathways of the universe were suddenly thrown open. The light, that had been trapped for hundreds of thousands of years, bouncing aimlessly in the cage of plasma, was suddenly released. It surged forward in every direction, a wave of brilliance moving at the speed of light, carrying with it the imprint of that final moment of scattering. This ancient flash is what we now detect as the cosmic microwave background. It is the afterglow of the Big Bang, the wall of fire finally breaking apart to let the universe breathe. If you had eyes that could survive that moment, you would have seen the blinding white fog dissolve into a clarity that stretched to infinity. The universe became transparent, but this moment of liberation contained the seeds of a profound isolation. The release of the cosmic microwave background was a one-time event. It was the fading heat of the initial explosion, destined to stretch and cool until it became invisible to the naked eye. Once that initial flash passed, there was nothing left to replace it. The universe was now clear, but it was also empty of sources. There were no stars to shine. There were no galaxies to spin. There were no quasars to beacon across the dark. There was only the newly formed hydrogen gas, cooling rapidly in the expanding void. The brilliance of the plasma era was gone, replaced by a dull, warm glow that was rapidly fading into black dot. We often speak of the darkness of space as a passive backdrop, but the darkness that fell upon the universe after recombination was a heavy, physical weight. It was the darkness of absence. The stage had been set. The curtains had been pulled back. The air was clear, but there were no actors. The light had escaped, fleeing to the edges of the cosmos, and in its wake, it left a silence so absolute that it is difficult for the human mind to grasp. This was the beginning of the cosmic dark ages. It was not merely a night. It was an epoch of invisibility. The universe was filled with matter-vast clouds of hydrogen and helium drifting in the void, but without a source of energy to ignite them, they remained hidden. The gas was neutral, stable, and cold. It did not emit light. It did not reflect light. It simply existed, a suffocating ocean of unseen particles, expanding into the nothingness. The transition from the blinding plasma to this absolute dark was the most dramatic shift in visual history. We went from a universe that was entirely light to a universe that was entirely shadow. And this shadow was not fleeting. It would not last for a night, or a season, or a century. The dark descended and held its grip for hundreds of millions of years. To the human eye, this era would have appeared as a void of infinite duration. If you were an immortal observer drifting through the cosmos during the Dark Ages, you would see nothing but a profound, suffocating blackness in every direction. Centuries would pass, then millennia, then millions of years, without a single spark to break the monotony. The universe seemed to have fallen asleep, its initial burst of energy spent, leaving behind a cooling corpse of gas, expanding aimlessly into the forever. But this stillness was an illusion. The darkness was not empty. It was pregnant with potential. While the electromagnetic force, the force responsible for light, heat, and chemistry, had fallen silent, the oldest and most patient force in the universe was quietly going to work. Gravity does not require light to function. It does not need a transparent medium or a witness. It operates in the dark, reaching across vast distances to bind matter together. In the aftermath of the Big Bang, as the fires faded and the fog of the early universe cleared, gravity became the primary architect of reality. It was the invisible hand sculpting the raw materials of creation, preparing the stage for the drama that was yet to come. And to understand how gravity built the universe we see today, we must look at the canvas it was given. The gas that filled the universe after the Great Clearing was not perfectly smooth. If the distribution of hydrogen had been perfectly uniform, every cubic meter of space contained exactly the same number of atoms as every other cubic meter of the universe, would have remained dead forever. In a perfectly balanced system, the pull of gravity is equal in all directions. Every atom would be tugged with the same force from every side, resulting in a net movement of zero. The gas would simply have continued to expand and cool, thinning out until it was little more than a whisper in the void, never collapsing to form a star, never clustering to form a galaxy. Fortunately, the universe was born with imperfections. Deep in the quantum history of the Big Bang, tiny fluctuations occurred, microscopic ripples in the density of reality itself. When the universe expanded, these microscopic ripples were stretched across light years, creating vast regions of space that were ever so slightly denser than others. These were not dramatic clumps. They were incredibly subtle variations, mere shadows of mass where the gas was perhaps a fraction of a percentage point thicker than the surrounding emptiness. But in the delicate mechanics of the early cosmos, this slight imbalance was everything. These regions of higher density acted as gravitational seeds. Because they contained slightly more mass, they exerted a slightly stronger gravitational pull than the regions around them. Slowly, they began to draw in the surrounding hydrogen. It was a process of accumulation that defied the human perception of speed. It was a drift, a gentle gathering of atoms in the dark. A single hydrogen atom, drifting in the void, would feel the faint tug of a distant cloud and begin a slow, spiraling fall toward it. This was the mechanics of silence. There were no explosions, no collisions of tectonic plates, no roaring winds. There was only the silent infall of gas. Across billions of light-years the universe was separating itself. The regions that started slightly empty were becoming emptier, evolving into the great cosmic voids that exist today, vast bubbles of nothingness, millions of light-years across. The regions that started slightly dense were becoming denser, hoarding the fuel that would one day light up the night. We must also understand the chemical simplicity of this time. To us, matter is complex. We're accustomed to a world built from a rich periodic table: carbon for biology, silicon for rocks, iron for blood, oxygen for breath, gold for jewelry. We live in a universe cluttered with heavy elements. But during the Dark Ages, none of these things existed. The universe was chemically sterile. The Big Bang was efficient, but it was not a chemist. It produced only the simplest, most stable nucleus. The cosmos was composed almost entirely of hydrogen, about 75%, and helium, about 25%. With a trace dusting of lithium, there was no dust. There were no ice crystals. There were no rocky asteroids. If you could have scooped up a handful of the early universe, it would have slipped through your fingers as a pristine, colorless gas. This purity defined the physics of the era. In our modern universe, gas clouds can cool down efficiently because they are dirty. They contain carbon monoxide and dust grains that radiate away heat, allowing the cloud to collapse quickly. But the primordial gas was clean. It had no heavy elements to help it radiate away its thermal energy. This made the work of gravity incredibly difficult. As the gas clouds fell inward, they naturally heated up. Pressure creates heat, and this internal heat created an outward pressure that fought against gravity. That gas wanted to expand back out just as much as gravity wanted to pull it in. This tug-of-war slowed the growth of structure to a crawl. The universe was caught in a delicate balance between the thermal energy of the gas and the gravitational pull of the dark matter halos in which it sat. It was a stalemate that lasted for hundreds of millions of years. Is why the Dark Ages were so long. The universe was struggling to overcome its own temperature, struggling to squeeze the simple hydrogen gas tightly enough to force a reaction. And so, the cosmos waited. The temperature of the background radiation continued to drop. The universe expanded, stretching the distance between these growing clouds. The cold deepened. We speak of the cold of space today, but the cold of the Dark Ages was a different species of temperature. It was approaching absolute zero, a state of minimal vibration where the universe held its breath. In this deep freeze, the giant clouds of hydrogen protogalactic halos began to settle. They were colossal, spanning thousands of light years, yet they were invisible. They emitted no light because they were not hot enough to glow, and they reflected no light because there was nothing to reflect. They were merely massive concentrations of matter defined only by their weight. If you had a spaceship capable of navigating this era, your sensors would be useless. Radar would find nothing to bounce off. Optical cameras would see only black. But if you had a gravitational sensor, the screen would light up. You would see the universe as a web, a vast, three-dimensional lattice of filaments connecting massive nodes of gas. You would see the skeleton of the cosmos, the underlying structure that dictates where every galaxy, every star, and every planet is located today. This invisible lattice is the most important structure in science. It is the scaffolding of reality. The galaxies we see today are merely the fairy lights draped over this dark, ancient framework. During the Dark Ages, the scaffolding was being erected in total secrecy. The gas was pooling into the gravitational wells, flowing along the filaments like water running down a wire, collecting in the nodes. This accumulation created a unique problem for modern astronomers. We are trying to study a period of history where the primary actor-neutral hydrogen is notoriously antisocial. Neutral hydrogen is an efficient absorber of ultraviolet light. It is a fog. Even if there were faint sources of energy trying to spark into existence, the surrounding blanket of neutral gas would have smothered their signal immediately. The universe was not just dark. It was opaque to the specific frequencies that usually signal the birth of stars. We call this the 21-centimeter line, a specific wavelength of radio emission that neutral hydrogen gives off when the spin of its electron flips. It is an incredibly faint, low-energy signal. A single atom might emit this signal once every 10 million years, but because there was so much hydrogen, because the entire universe was essentially a single ocean of it, these faint signals combined to create a background hum. This hum is the song of the Dark Ages. It is the only signal that escaped the silence. To break this silence, and to penetrate the wall of neutral hydrogen that stood guard over the early universe, humanity had to fundamentally alter the way it observed the sky. For 400 years, ever since Galileo first ground a piece of glass and pointed it at Jupiter, astronomy was defined by the capture of visible light. We built larger lenses, then larger mirrors, effectively creating giant mechanical versions of the human eye. We were obsessed with gathering more light, sharpening the image, and magnifying the faint glimmers of the night. This approach culminated in the Hubble Space Telescope, a machine that revolutionized our understanding of the cosmos. Hubble peeled back the layers of the nearby universe, showing us the violent beauty of nebulae and the majestic structures of distant galaxy clusters. But even Hubble, with its pristine view from above the atmosphere, eventually hit a wall. When it stared into the deepest patches of space, trying to find the very first galaxies, the images faded into black. It was not a failure of optics, it was a failure of physics. Hubble was designed primarily to see the same light we see through visible spectra, with a slight extension into the ultraviolet and the new. But as we established, the light from the beginning of time is no longer visible. The expansion of the universe has stretched it, pulling it out of the range that glass lenses and traditional sensors can detect. The signals from the Dark Ages were washing over Hubble's mirrors, but the telescope was blind to them. It was like trying to catch a radio wave with a butterfly net, to see the era where nothing existed. We did not need a better camera. We needed a different kind of sense entirely. We needed to stop looking for the flash of starlight and start looking for the faint, residual warmth of creation. We needed a time machine built specifically to harvest the infrared. This necessity birthed the concept of the James Webb Space Telescope. From the very first sketches, this machine was not intended to be a successor to Hubble in the traditional sense. It was designed to cover the blind spot of its predecessor. The engineering required to achieve this was an exercise in contradictions. To detect the heat of the first star's objects that burned with a ferocity we can scarcely imagine, we had to build a machine that was arguably the coldest object in deep space. Infrared light is, in essence, heat radiation. Everything emits it. The Earth glows in infrared, the sun blazes in it. Even our own bodies radiate it constantly. If you were to place an infrared telescope on the surface of the Earth, or even in a low orbit where the planet occupies a large portion of the sky, the telescope would be blinded. It would be like trying to take a photograph of a firefly while standing in the middle of a forest fire. The heat of the telescope itself, the heat of the instruments, and the heat of the Earth would swamp the faint, dying signals arriving from the edge of the universe. Therefore, the architecture of the James Webb Space Telescope was dictated by the need for aggressive, absolute cold. The mission required sending the observatory to a specific gravitational parking spot, known as Lagrange Point 2, located 1.5 million kilometers away from Earth, 4 times the distance to the Moon. Here, far from the radiant heat of our home planet, the telescope could turn its back on the sun and face the freezing void. But distance alone was not enough. To catch a photon that has traveled for 13.5 billion years, the detector must be quieter than the signal it is trying to catch. If the atoms in the telescope's mirror are vibrating with thermal energy, that vibration creates noise. To silence the machine, engineers designed a sunshield the size of a tennis court, 5 layers of a specialized, aluminum-coated polymer called kapton. These layers are thinner than a human hair, yet they perform a thermodynamic miracle. On the side facing the sun, the shield is bombarded by solar radiation, reaching temperatures hot enough to boil water. On the other side, in the permanent shadow, the temperature plunges to nearly absolute zero, roughly minus 233 degrees Celsius. In this deep freeze, the electrical noise of the atoms quiets down. The vibration stops. The telescope becomes a dark, cold trap, waiting for the warmth of the early universe to fall into it. His extreme temperature is why the telescope looks the way it does. It is not a tube like Hubble. It is an open, naked array of mirrors sitting on a silver raft. The mirrors themselves are a testament to the specific requirements of infrared astronomy. They are coated in a microscopic layer of gold. While silver or aluminum are excellent for reflecting visible light, gold is the supreme reflector of infrared. It captures the long, stretched-out wavelengths with near-perfect efficiency, guiding them into the sensors. The choice of infrared was not merely about overcoming redshift. It offered a secondary, crucial advantage in our quest to understand the dark ages, the early universe. As it began to form structures, it was not just a clean expanse of gas. As the first stars lived and died, they began to pollute the cosmos with dust. Cosmic dust is the bane of visible astronomy. It is a thick, opaque smoke that blocks starlight, hiding the nurseries where stars are born. When we look at the Milky Way on a clear night, the dark patches we see are not empty space. They are clouds of dust blocking the view. Visible light, with its short, tight wavelengths, crashes into these dust grains and is scattered, much like the headlights in the fog we described earlier. But infrared light is different. Its wavelengths are longer, looser, and more fluid. They have the ability to slip around the dust grains, passing through the clouds as if they weren't there. By viewing the universe in the infrared, the James Webb Space Telescope effectively makes the dust transparent. It allows us to peel away the curtain of the nebulae and look inside the delivery rooms of the cosmos. This was essential for the mission. We knew that the era following the Dark Ages, the Era of Reionization, was messy. It was filled with the debris of the first generations of stars. If we had tried to view it in visible light, even without the redshift problem, we would have seen only the outer shells of the clouds. With the infrared eye, we could look into the core. We could see the heat of the protostars glowing inside their cocoons. So the machine was built as a hunter of two things: the redshifted ghosts of the first light and the thermal signatures of stars hidden behind walls of dust. It was an instrument of immense sensitivity. To give you a sense of the precision involved, if you were to place a bumblebee on the surface of the moon, at the distance of the Earth, the James Webb Space Telescope would be able to detect the body heat of that bee. It was this level of sensitivity that was required to stare at a patch of nothingness and find the something that had been hiding there all along. The journey to launch this observatory was a saga of delay and anxiety, precisely because the tolerances were so unforgiving. Unlike Hubble, which sits in low Earth orbit and could be serviced by astronauts, Webb was headed for the deep isolation of L2. There was no repair crew. There was no second chance. The telescope had to fold itself up like a piece of complex origami to fit inside the rocket fairing, and then, slowly, meticulously, unfold itself in the vacuum of space while traveling 1,000,000 miles an hour. The deployment sequence involved over 300 single-point failures, mechanisms that, if they jammed or broke, would turn the $10 billion observatory into a piece of space junk. The sun shield had to tension itself perfectly. The secondary mirror had to swing out and lock. The 18 segments of the primary gold mirror had to align with a precision measuring less than a fraction of the width of a bacterium. After the terror of the deployment, after the mirrors had unfolded and the sun shield had tightened into its diamond shape, a profound quiet settled over the mission. The telescope was safe, suspended in the gravitational stillness of Lagrange Point 2, but it was not yet ready to see. For months, the observatory had to cool. It was a slow, agonizing drift down the thermometer, waiting for the gold mirrors to shed the latent heat they had carried from Earth. The engineers on the ground could do nothing but watch the telemetry, waiting for the instruments to reach the cryogenic temperatures necessary to detect the faint infrared whispers of the early universe. It was a period of dormant anticipation, a long intake of breath before the eyes opened. When the moment finally arrived to select a target for the first public reveal, the astronomical community returned to a philosophy that had revolutionized our understanding of the cosmos 30 years prior, the concept of the deep field. To understand the significance of what James Webb was about to do, we must remember the gamble taken by the Hubble Space Telescope in the mid-90s. At that time, astronomers decided to point the most expensive camera ever built at a patch of sky that appeared completely empty. It was a tiny speck of darkness, no larger than a grain of sand held at arm's length. Devoid of any known stars or galaxies, critics argued it was a waste of precious observing time, predicting that the telescope would simply return a picture of black noise. But when the shutter remained open for days, soaking up the light, that tiny grain of darkness erupted into a tapestry of thousands of galaxies. It proved that the universe was not empty, it was crowded. Every patch of the void, it was teeming with islands of stars. The Hubble Deep Field taught us that if you look hard enough at nothing, you will eventually find everything. But James Webb was built to go beyond the everything that Hubble saw. It was built to find the something that existed before the everything. The target chosen for this first deep look was a massive cluster of galaxies known as SMACS 723. To the untrained eye, this choice might have seemed odd. The goal was to see the earliest universe, yet the telescope was pointed at a cluster of galaxies that was relatively close, only about 4 billion light-years away. But this was a strategic decision, utilizing one of the most elegant tricks. In the laws of physics, gravitational lensing, gravity is not just a force that holds planets in orbit. It is a force that warps the fabric of space itself. When a massive object like a cluster of thousands of galaxies sits in the foreground, its combined gravity creates a valley in space-time. As light from the distant background travels toward us, it falls into this valley and bends, much like light bending through a glass lens. The galaxy cluster acts as a natural, cosmic magnifying glass. It amplifies the light of the objects behind it, brightening them and stretching them out, allowing us to see things that are far too faint and far too distant for any telescope to see on its own. By pointing James Webb at this cluster, astronomers were effectively placing a telescope on top of a telescope, stacking the power of human engineering on top of the power of natural gravity. The exposure began. For 12.5 hours, the telescope stared at this single patch of sky. It was a blink of an eye compared to the weeks-long exposures Hubble used to take. Yet in that short window, Webb gathered more light than its predecessor could have collected in a month. The gold mirrors drank in the photons. The new camera converted the heat signatures into digital data, layer by layer, wavelength by wavelength. Down on Earth, the data was processed. The infrared frequencies shifted into visible colors so that human eyes could comprehend the image. When the final composite was revealed, the reaction was not just scientific validation. It was a visceral shock. The image did not look like the gradual, misty dawn astronomers had expected. It looked like a jewelry box spilled onto black velvet. The density of the image was overwhelming. In the center blazed the white, elliptical galaxies of the foreground cluster, glowing with the fierce light of billions of mature stars. Scattered among them were bright, spiky points of light, individual stars within our own Milky Way, sitting in the foreground like dust on a camera lens, their 6-pointed diffraction spikes, announcing the hexagonal shape of the Webb's mirrors. But the eyes of the scientists did not linger on the bright lights. They were drawn to the background. Behind the cluster, filling every available gap in the darkness, was a chaotic swarm of red and orange shapes. There were thousands of them. Some were smeared into long, thin arcs, curved around the center of the image like brushstrokes in a Van Gogh painting, the signature of gravitational lensing, where the light of distant galaxies had been stretched and warped by the mass of the cluster. Others were tiny, distinct red dots, glowing faintly against the absolute black. These were the targets. These were the ghosts. The redness of these smudges was the visual proof of the journey they had undertaken. Their light had been stretched by the expansion of the universe for over 13 billion years, shifting from the ultraviolet and visible light of their birth into the deep infrared captured by the telescope. We were looking at galaxies as they existed when the universe was less than 1 billion years old. The expectation, built on decades of standard cosmological models, was that at this depth, the universe would be simple. Models suggested that the first galaxies would be small, ragged, and dim tentative collections of gas barely holding themselves together, slowly lighting up the dark. We expected to see a turn-on phase, a gradual brightening where the darkness gave way to a few lonely outposts of light. Instead, the first deep field revealed a metropolis. The background was not empty, it was full. It was teeming with structure. The sheer number of galaxies visible in that single grain of sand patch of sky implied that the early universe was far more active, far more efficient at building stars, and far more populated than anyone had dared to predict. It was an immediate assault on the idea of the Dark Ages as a long, quiet slumber. It appeared that the universe had woken up quickly, and it had woken up violently. As astronomers zoomed in on the faintest red specks, the anomalies began to pile up. These were not the shapeless blobs of gas that theory predicted. Even at these extreme distances, some of the galaxies appeared to have structure. They had dense cores, they had hints of spiral arms, they had defined edges. They looked impossibly mature. It was as if we had looked into a nursery expecting to find infants, and instead found fully grown adults sitting in the cribs. The silence of the void was replaced by the noise of data. Each of those red smudges contained millions, perhaps billions of stars. Each represented a localized island of order that had managed to defy the chaos of the early universe, to pull itself together. The visual fidelity of the Webb image was so high that it didn't just show us that they were there. It allowed us to begin asking what they were. The psychological impact of this first image cannot be overstated. For years, the Dark Ages had been a theoretical construct, a blank chapter in the history book of the universe labeled "Here There Be Dragons." We assumed that if we could see into it, we would find a vast, thinning fog with a few sparks. But the Webb deep field tore that page out of the book. It showed us that the timeline of creation might be far more compressed than we realized. The lights didn't flicker on one by one. They seemed to have burst into existence in a torrent. The clarity of the image also brought the concept of nothing into sharp relief. In the spaces between the bright cluster galaxies, and even between the red arcs of the ancient background, the deep blackness remained. But now, that blackness felt smaller. It felt besieged. The deeper we looked, the more we realized that empty space is a misnomer. The universe is a machine for making galaxies, and it started its work almost immediately. But as the initial euphoria of the visual spectacle began to fade, a different sentiment took hold within the quiet offices of theoretical astrophysics. The astronomers moved past the beauty of the deep field and began to analyze the raw numbers hidden within the light. They measured the brightness, they calculated the distance, and most importantly, they estimated the mass of the red smudges that littered the background of the image. And as the calculations poured in, the mood shifted from celebration to a deep, unsettling confusion. The universe we saw in those images did not match the universe we had built in our equations. To understand why these discoveries were so disturbing, we must revisit the standard blueprint of cosmic history. For decades, cosmology has relied on a theory known as hierarchical assembly. This is the idea that the universe was built from the bottom up, like a child constructing a castle out of sand. It posits that in the early universe, the era of the Dark Ages and immediately following gravity was only strong enough to pull together very small clumps of matter. The first structures should have been tiny, messy, irregular dwarf galaxies little more than star clusters, containing perhaps a few million solar masses. According to this model, these small clumps would slowly drift toward one another over billions of years, merging and crashing together to form larger structures. A spiral galaxy like our Milky Way, with its distinct arms and massive central bulge, is not supposed to be a starter home. It is supposed to be a mansion, the result of billions of years of renovations, additions, and mergers. To find a fully formed, massive galaxy in the first few 100 million years of the universe would be like walking onto a construction site 10 minutes after the groundbreaking ceremony and finding a completed 100-story skyscraper standing against the sky. It defies the logic of cause and effect. It defies the speed at which construction, or in this case, gravity, can physically operate. Yet this is exactly what James Webb found. Buried in the high redshift data were a handful of galaxies that simply should not exist. They were located at a point in time roughly 500 to 700 million years after the Big Bang. In human terms, if the universe were a 100-year-old man, these galaxies existed when he was a toddler of 3 or 4. Standard theory dictates that, at this age, the universe should be filled with proto-galaxies, small, faint, chaotic blobs. But the telescope returned data on 6 specific galaxies that were terrifyingly massive. These objects, quickly dubbed the universe breakers, by the scientific press, possessed masses comparable to our modern Milky Way. They contained tens, perhaps hundreds of billions of stars. But unlike the Milky Way, which spreads its stars out over 100,000 light-years, these ancient giants were compact. They crammed all that mass, all those billions of suns, into a sphere, a fraction of the size of our galaxy. They were dense, bright, and red, glowing with an intensity that suggested they had already converted huge amounts of gas into stars. The existence of these impossible galaxies creates a crisis of time. Star formation is not an instantaneous process. It takes time for gas to cool, collapse, and ignite. It takes time for the first generation of stars to live, die, and enrich the surrounding gas with heavier elements. It takes time for gravity to marshal enough material from the surrounding void to build a structure weighing as much as 100 billion suns. When cosmologists ran the simulations backward, trying to figure out how these galaxies could have formed, they hit a mathematical wall. To get that much mass in one place so quickly, the gas would have had to collapse at a rate that is nearly perfectly efficient. It would mean that almost every atom of hydrogen in that region of the universe fell into the galaxy and turned into a star instantly, without any waste, without any feedback, without any pause. This contradicts everything we know about how stars form. In the local universe, star formation is messy and inefficient. When a cloud of gas collapses to form a star, the new star turns on and blasts the remaining gas away with intense radiation and stellar winds. It is a self-regulating process. The birth of a star pushes away the fuel needed to make more stars. This slows down the growth of galaxies. It is a natural brake pedal. But the universe breakers seem to have no brake pedal. They suggest a mode of growth that is voracious, rapid, and unhindered by the physics we observe today. The implications are profound. If these measurements are correct, we are missing a fundamental piece of the puzzle. It suggests that the nothing of the Dark Ages was not a quiet period of slow accumulation, but a time of rapid, runaway collapse. It forces us to ask if the seeds of these galaxies, the density fluctuations discussed in Chapter 3, were much larger than our theories of the Big Bang predict, or perhaps gravity itself behaved differently in the early universe, pulling matter together with a strength that has since faded. We are faced with a stark choice. Either our clock is wrong, or our understanding of gravity is wrong. Some theorists have even floated the radical idea that the universe might be older than 13.8 billion years, that the timeline we have carefully constructed from the cosmic microwave background is somehow calibrated incorrectly, and these galaxies had twice as much time to grow as we think they did. But there is another possibility, one that is equally intriguing. Perhaps we are misinterpreting what we are seeing. These galaxies are so distant that they appear as mere points of light. We are inferring their mass based on their brightness. We assume that light equals stars. But what if something else is generating that light? What if deep inside these impossible giants there lies a different engine, a monster of the dark, that is mimicking the light of a billion stars? The tension in the scientific community is palpable. We built a machine to see the beginning, expecting to find a nursery of delicate, forming things. Instead, we found a forest of ancient oaks where there should have been saplings. The universe did not ease into existence. It seems to have roared into being, fully formed and heavy with matter. The transition from the fog of the Dark Ages to the era of galaxies was not a slow sunrise. It was an explosion of structure. And this brings us to the edge of our understanding. If gravity alone cannot explain how these structures grew so big, so fast, we must look at the hidden partner in this cosmic dance. We must look at the invisible scaffold that holds the visible matter together. We must question the role of dark matter. There is a seduction in the power of a tool like the James Webb Space Telescope. When we see it peel back the layers of dust, when we watch it resolve the chaotic smudges of the impossible galaxies into defined structures, we are tempted to believe that our vision is now limitless. We begin to feel that if we simply built a mirror large enough, or integrated the light for long enough, we could stare all the way back to the moment of creation itself. We imagine a continuous film reel of history, rewinding smoothly from the present day to the Big Bang. But the universe does not grant us this infinite access. No matter how perfect our engineering, no matter how cold we chill our senses, we eventually collide with a horizon that cannot be crossed by glass or gold. We hit the hard wall of the observable. This wall is not defined by the failure of our technology. but by the failure of the medium itself. We must remember that astronomy is, at its core, the study of light. We are dependent on photons, those tiny packets of energy to act as messengers, carrying information from the past to the present. If an era of history did not create these messengers, or if the messengers were destroyed before they could begin their journey, that era remains utterly invisible to us. The James Webb Space Telescope is a master of the infrared, a hunter of heat and ancient starlight, but it cannot see what isn't there. And as we push beyond the era of reionization, beyond the universe breakers, and into the deepest recesses of the cosmos, we enter a time where the universe stops sending postcards. We are returning to the true cosmic dark ages, but this time, we view it not as a period of formation, but as a visual barrier. We must distinguish between the darkness of space that is merely far away and the darkness that is absolute. The galaxies we discussed in previous chapters, those red, ancient giants, are the furthest outposts of the visible world.
They represent the edge of the map. Beyond them lies a gap in the record, a stretch of time lasting hundreds of millions of years where the universe was chemically and physically incapable of generating the kind of light a telescope can detect. To understand this limit, we must look at what lies behind the dark ages. If we point our telescopes past the furthest galaxy, past the last wisp of gas illuminated by the first stars, we do not see empty blackness. We see a wall of fire. This is the surface of last scattering, the visual boundary of the universe. It is the face of the primordial fog we identified in the early chapters, the moment when the universe cooled enough to become transparent. When we look at this surface, which we detect today as the cosmic microwave background, we are looking at the most distant object in the cosmos. But we are not seeing the beginning. We are seeing a curtain. Imagine standing in a thick fog bank that suddenly clears. You can see the edge of the fog, the precise wall where the mist ends and the clear air begins. But you cannot see into the fog. You cannot see what lies buried deep inside the mist, nor can you see the source that created it. The surface of last scattering is that wall of mist. It is an opaque shield standing 380,000 years after the Big Bang. Anything that happened before that moment, the singularity, the inflation, the churning of the quark-gluon plasma, is hidden behind this wall of light. We can calculate what happened, we can theorize it, but we can never, ever see it with a telescope. The photons from the Big Bang are trapped inside the wall, scattered into oblivion, their information scrambled forever. So, we are sandwiched. On one side, we have the wall of fire at 380,000 years. On the other side, we have the first galaxies appearing perhaps 300 or 400 million years later. Between these two landmarks lies the gap. This is the true abyss. It is a period of history where the universe had cooled down from the fire of creation but had not yet lit the fire of the stars. It was a universe of warm, neutral gas, slowly fading into a deep, cryogenic freeze. This gap poses a profound existential frustration for cosmologists. We know that the most critical events in the structural history of the universe happened right here, in the dark. This was the era when the seeds of the impossible galaxies were sown. It was the era when dark matter halos collapsed. It was the era when the blueprint of the modern cosmos was drawn. Yet, it is the one era we cannot watch. There were no stars to shine. There were no quasars to beacon. The hydrogen gas was neutral, meaning it did not emit light, it simply sat there, heavy and silent. If you were to drift in this void, you would be blind. The wall of fire would be far in the distance, fading into the infrared and eventually into radio waves, becoming invisible to the naked eye. The future stars were not yet born. You would be suspended in a nothingness so complete that the concept of sight would lose its meaning. For a telescope like Webb, which relies on contrast, on seeing a bright object against a dark background, this era is a blank canvas. There is no contrast. There is only the uniform, suffocating hum of hydrogen. This is the ultimate physical horizon. It forces us to accept that our visual history of the universe has a missing reel. We have the opening credits, the Big Bang/CMB, and we have the movie starting from the second act, the first Galaxies, but the first act, the character development, the setting of the scene, the initial conflicts, is lost in the dark. We are trying to reconstruct the most important part of the story based solely on the aftermath. We look at the universe breakers and ask, how did you get so big so fast? But we cannot watch them grow. We can only see the result. The limits of light also extend to the geometry of the universe itself. Even if we could see into the dark, the expansion of space is working against us. As we look deeper, we are looking at light that has fought a losing battle against the stretching of the cosmos. There comes a point where the expansion is so rapid, the distance so vast, that the light is stretched not just into the infrared, but into radio waves so long and so weak that they become indistinguishable from the background noise of the universe. The signal becomes a whisper in a hurricane. We are approaching the boundary of knowledge where observation must give way to inference. We are moving from the realm of photography to the realm of archaeology. We are no longer snapping portraits of the ancestors, we are sifting through the dirt, looking for microscopic clues that might tell us how they lived. The James Webb Space Telescope has brought us to the very edge of the illuminated world. It has shown us the first lighthouses on the shore. But it cannot show us the ocean at night. However, science does not accept invisible as a final answer. If the eyes fail, we must learn to listen. If the photons of visible and infrared light are absent, we must hunt for a different kind of particle, or a different wavelength that survives the dark. The universe is never truly silent, even in the deepest sleep of the Dark Ages, the atoms were humming. And it is this faint, monochromatic hum that represents our only hope of mapping the invisible room. We have now cast our vision across the entirety of the observable stage. We began this journey standing on the surface of a small, rocky world, looking up with biological eyes evolved for survival, trying to impose patterns on the scattered stars of the night sky. We extended that vision through glass lenses, then into the cold vacuum of space with the Hubble, and finally, we built a machine of gold and cold to peer into the infrared silence of the deep past. We have traveled back through the layers of time, past the mature spirals of the modern epoch, through the chaotic mergers of adolescence, into the violent clarity of the Era of Reionization, and finally, into the dense, suffocating fog of the Dark Ages. We have walked up to the edge of the physical horizon, the wall of last scattering, and stared into the face of the absolute unknown. And now, standing at the end of this intellectual voyage, we must turn around. We must look back at the path we have charted and ask what the silence has actually told us. When we set out to look at the nothing that existed before the stars, we carried with us a specific human bias. We equate darkness with emptiness. We equate silence with absence. We assumed that because the early universe was dark, it was also dormant, a vast, sleeping ocean waiting for the first light